exponential equation. Here it is. It is 7 to the power of 3x minus 1 is equal to 61. Okay, guys. Now, it's not going to be easy at all to try to get the same base like we were earlier. Strategy number 1 is not really going to work for us. So let me show you a different strategy. Okay, strategy number 2 is to log both sides. Okay, let me introduce this strategy like this. What are you trying to solve for? You're solving for x, and x happens to be part of your power, part of the exponent. So really, if you're trying to solve for x, you need this variable x to come down so that you can solve for it. And you remember from the previous lesson that you have a power rule that will bring down a power. But before you use the power rule, you're going to have a log in front of this exponential expression. So you may want to peek back on chapter 4, section 5, and look over the power rule. It says when you take the logarithm of an exponential expression, then the power can come down. So let's take log of both sides, okay? Now, you could take log, base, whatever on both sides. It's completely up to you. The common thing to do is to take a common log to both sides. So that's what I'll do. And of course, if you take a logarithm of the left, you have to take the log of the right as well. Okay, the power rule says that now this power, 3x minus 1, is allowed to come down in front of this equation. So it's going to be 3x minus 1. I need parentheses around it because it's more than one term, times log of 7 is equal to log of 61. Okay? All right. Now, log 7 is just a number. Log 7 is log 7, do you know what that is? It's the exponent to which you raise 10 to get 7. Log 7 is the exponent to which you raise 10 to get 7. At the end of the day, it's just a number. So what I want you to do to that number is to distribute that number so that you no longer have parentheses, okay? So we're distributing. So you get 3x times log 7 minus 1 times log 7 is equal to log of 61. Okay? Now, this term here is the only one that has a variable. So this is like my variable term. This term doesn't have a variable term, so it's like a constant term. So you need to move that to the other side. How? By doing the opposite of subtraction, addition. So you're going to see me right now add log 7 to both sides. Like that. Okay, I'm trying to isolate my variable. Cool. So this is what you have. 3x times log 7 is equal to log 61 plus log 7. Okay? Cool deal. Now, to wrap this up, all we need to do is divide both sides. Let's see if I can do this here. Divide both sides by everything except for the variable. So divide both sides by 3. Also divide both sides by log 7. 3 times log 7. Okay, cool. So what that does for you on the left is, these 3's divide out, log 7 divides out. So then all you're left with on the left is just x. And on the right, you got log 61 plus log 7, all divided by 3 times log 7. This is your final answer. This is an exact answer. This is an exact answer. Okay? Now you want to punch all of this into your calculator, right? And get an approximation. Okay, so when you do this, be careful. This is what I encourage you to do. Okay? Punch in log 61. All right, that's going to give you some decimal. And then add to that log 7. Press equals. And then divide by, open up a set of parentheses, and divide by 3 times log 7. 3 times log 7, okay? So if you do all of this correctly, you should get approximately 1.0375. I'll just cut it off right there. It's a long decimal that never stops, so I'm going to cut it off right there. It's about that number there, all right? Punch it into your calculator and see how you do. All right, guys, example 3. Solve the exponential equation 2 times 5 raised to the power of x minus 4 plus 7 is equal to 31. Okay, before you consider taking, getting the common base, which is strategy 1, or strategy 2, logging both sides, before you do any of that, I suggest you isolate this exponential expression right here. Isolate this exponential expression. To start isolating this exponential expression, move 7 to the other side of the equation using subtraction. Okay? When you subtract 7 from 31, you get 24. The next thing I suggest you do is to divide both sides by 2. Okay? When you divide 24 by 2, you get 12. Cool. Now on the left-hand side, you have just one term here, one exponential expression only is equal to a constant. Now, strategy 1 is not going to work for us to get the same base on both sides. So let's use strategy number 2, which is log both sides. Okay, log both sides. Now, I told you that you can take any kind of log you want. Log base 10, which is what I'm doing. Log base 7, log base whatever. You could even do a natural log of both sides if you want. All right. The most common thing to do is to take a common log or a natural log. That way we can use our calculator later. To at the end to approximate our answer. Okay, now that I've taken the common log of both sides, you know that the exponent comes down. Okay, like this. We can distribute this log 5, which is just a number, right? Distribute. You don't have to distribute, by the way. I believe our book at this point just divides both sides by log 5. That's fine as well. Okay, so you're going to have x times log 5 minus 4 times log 5 is equal to log of 12. Okay. All right, cool. I'm going to move this screen down, or move it up rather. Okay, so I think what we want to do now is notice that this term here doesn't have a variable. This one does, so this is a variable term. This one's a constant term, therefore. So let's add it to the right-hand side, okay? So I'm going to add 4 times log 5 to both sides. Okay? So what that's going to do for us now, you know, that cancels. And so on the left side, we have just x times log 5. On the right, I have log 12 plus 4 times log 5. Cool. And then just divide both sides by log 5. That's a number. Divide both sides by log 5. So your final answer, and this is an exact answer, x is exactly equal to log of 12 plus 4 times log of 5, and then all of that divided by log of 5. Okay? Hey, don't make the mistake of trying to divide out these log 5s. You cannot do that because you have a sum of terms in the numerator. Okay? All right, so this is your final exact answer. If you want an approximation, I suggest you punch all of this into your calculator, do log 12, and then add to that, you may want to open a set of parentheses, 4 times log 5. I would probably press equals at that point, and then divide all of that by log 5. I'll write down the approximation value right now. Okay, on my calculator, I actually got 5.543959311. I just decided to round to 3 decimal places this time, so 5.544 approximately equal to that. All right, cool deal, guys. Let's move forward. All right, we got 4 to the power 2x minus 1 minus 5 is equal to 21. Similar to the previous example, I want to try to isolate my exponential expression, so I'm going to add 5 to both sides. That will give me 4 to the power 2x minus 1 is equal to 26. Now, I'm not going to be able to use strategy 1, which is get the same base on both sides. I'm going to log both sides. I'm going to change it up on this example just because I can. Instead of taking a common log of both sides, which is strategy 2, I'm going to take a natural log of both sides. It works the same way. There, I took the natural log of both sides. Now, by the power rule for logarithms, your power comes down like that, and you want to distribute natural log of 4, which is just an exponent, right? It's a number, and you can see how similar these examples are. Cool. And what you want to do next is maybe you want to add natural log of 4 to both sides. This is me trying to isolate the variable expression, okay? Isolate the variable expression. So now we have 2x times natural log of 4 on the left-hand side is equal to the natural log of 26 plus the natural log of 4, okay? And then just divide both sides. Why don't you just divide both sides by 2 natural log of 4, basically everything except the variable, 2 times the natural log of 4. Okay, so your final answer in an exact form is the natural log of 26 plus the natural log of 4, and then all of that over 2 times the natural log of 4. Good job. I'm going to scroll down and give you the approximation now. Okay, in a calculator, it's 1.675 approximately. I just want to be very clear that you need to be very careful when you're punching into your calculator. Do natural log of 26, add natural log of 4. I would say press equals, and then watch this. Divided by, open up a set of parentheses, and then type in 2 times natural log of 4, close all your parentheses, and then press equals. You should get this number. All right, good luck with that. Okay, next example, we have 10 raised to the power of 3x plus 1 is equal to 91. Okay, so let's, the left-hand side is just an exponential expression, so we can go ahead and use one of our strategies. We're not going to get the same base on both sides. It's not going to happen. So let's go ahead and take the log of both sides. I'm going to do common log. I think that would be a good idea. The reason why I think it's a good idea, especially in this example, is because you already have base 10 on the left-hand side. See, this is base 10, so it's a good idea to take log base 10 of an exponential expression that is base 10. That's a good idea, okay? All right, as opposed to a natural log. I think common log here would be better. All right, guys, this power comes down by the power rule for logarithms. Now watch this. This is what I wanted. Log of 10. This is a common log because the base is not written, so it's log base 10 of 10. It's asking you, what exponent do you raise 10 to get 10? To what exponent do you raise 10 to get 10? 1. Very good. So I'm going to replace, I'm not even going to distribute log 10 like we did in the previous examples. I'm not going to do this. I'm not going to do this. Let's distribute. No. I guess you could, but it's a waste of time. Log of 10 is just the number 1. 1 is the exponent to which you raise 10 to get 10. I hope that makes sense from earlier lessons. So then it's just 3x plus 1 is equal to log of 91. Let's subtract 1 from both sides to get 3x is equal to log of 91 minus 1. Yeah? And then divide both sides by 3. Log of 91 minus 1, all of that divided by 3. This is the exact answer. Let's get the approximation. So let's plug in log 91 and then subtract 1 from that number and then divide all of it by 3. Okay guys, I'm getting I'm getting approximately 0.31968. I don't know why I gave you so many decimal places, but whatever. That's what I'm getting. If there's more decimals after that, but I just cut it off at that point. All right? Cool deal. Look at this example. This one's pretty cool. 6,000 is equal to 200 times e raised to the power of 0.05x. Now, I know there's two letters, e and x, but only x is the variable. You know, e is a number that's approximately equal to 2.7. So what I suggest you to do in order to solve for this in order to isolate the variable expression, get this 200 out of there. How? By dividing both sides by 200. Okay? Cool. 200s are gone. Now look at this. Kill some zeros. And then just divide 2 into 6. How many times? 3 times. Good job. So then when you do the division, the arithmetic, you get 30 on the left-hand side is equal to just e raised to the power of 0.05x. Good job, everybody. Now, you're not going to get the same base on both sides. Strategy 1's not going to work. So do strategy number 2, which is log both sides. Now, I've been saying take whatever kind of log you want of both sides, and I still mean it. And in this example, since you already have base e on the right, it would make a whole lot of sense to take the natural log of both sides, because natural log is a logarithm whose base is e, and you already have base e here, so it's kind of giving you a hint. Take natural log. Okay? By the power rule for exponents, you know your power comes down. You don't need parentheses around it necessarily, because this is all just one term. Now, look at this, guys. This is the natural log of e right here. This is asking you for the exponent to which you raise e to get e. What exponent do you raise base e to get e? You know there's an invisible base e here, right? If you raise e to the power of 1, you will get e. So natural log of e is just 1. That's why I was recommending the natural log of both sides as opposed to the common log, because the natural log of e is just going to turn out to be the number 1. All right? Very similar to the previous example when you had the common log of 10. Log 10 just turned out to be 1, right? So all you got to do to solve for x is divide both sides by 0.05. So x is going to be equal to the left-hand side divided by 0.05. I'll write it like this. X is natural log of 30 divided by 0.05. Good job, you guys. Here's an approximation. All right, I'm getting approximately equal to 68.0239. How about that? Okay, here's the next one. Now, guys, I just want to say something. What makes this one more challenging is the fact, number one, we're going to have to take the log of both sides, okay, because you're not going to get the same base here. One base is 3, the other one is 4. So you're going to have to use strategy number 2. And we've never used strategy number 2 up to this point, where there's been a variable on the left and a variable on the right. Even if you look back at your previous examples, when we took the log of both sides, there's only been one variable. But now, when we take the log of both sides, there's a variable on both sides. So it's just going to make it more interesting. All right, here we go. We're going to take the log of both sides, all right? So log of the right-hand side and log of the left-hand side, okay? 3 to the power 2x minus 5. Okay, cool. Taking the log of both sides. What comes next is, remember the power rule for logarithm says that the powers can come down. So I'm going to bring the powers down. All right, cool. The powers have come down. Let me move the screen over just a little bit so we have some more space here. All right, so what you're going to see me do next is distribute both log 3, right, over here. And over here, you're going to see me distribute log 4. That's going to get rid of our parentheses, all right? So then this is going to turn out to be 2x times log 3 minus 5 times log 3 is equal to x times log 4 plus 1 times log 4. All right, cool. Now, I want to underline something. Any term that has a variable is called a variable term. So you got one right here, and you got one on the other side. Those are your variable terms, underlined in yellow. What I underline in green are your constant terms. They're constant terms because the green, what I've underlined in green, they don't have a variable at all, okay? So you got to get all your variable terms that are underlined in yellow on one side and all your constant terms, which are underlined in green, on the other. Okay, I'm going to recommend that you get all of your variable terms on the left and all your constant terms on the right. All right, so move your variable terms, maybe if you're going to do it like me, to the left. That means you're going to have to subtract this over to the left-hand side, okay? From both sides, of course. Subtract it from both sides. So on the right, obviously these, cancel out. And now the left-hand side becomes 2x log 3 minus x times log 4. Minus 5 times log 3, just bring that down, is equal to log 4. Okay, like that. Now, the next thing you're going to see me do is move this constant term over to the right using the opposite of subtraction, which of course is addition. So I'm going to add 5 log 3 to the right. Okay? All right. Now, what that gives us, after these cancel, right, is all of our variable terms on the left, so 2x times log 3 minus x times log 4. Those are your variable terms on the left. On the right, you have log 4 plus 5 times log 3. Those are your constant terms on the right, okay? Now, again, what you're trying to do is you're trying to solve for x, so you want to isolate x. So what I recommend you do at this point is factor out an x, a common factor of x from this left side. When you factor out an x from this term and from this term, what you're left with is 2 times log 3 minus log 4. Bringing down the right side. So then all you have to do at this point, let me erase this. This is supposed to be a 5. Make it look more like a 5, yeah. So all you have to do at this point is divide both sides by this number, 2 log 3 minus log 4. That's all a number right there. So you're going to see me divide both sides by that number, 2 log 3 minus log 4, right? Both sides, of course, 2 log 3 minus log 4. So you're going to see this entire factor divide out. And so all you're left with on the left-hand side is just x. So x is exactly equal to log 4 plus 5 log 3 in the numerator divided by 2 times log 3 minus log 4. This is an exact answer. That's an exact answer. If you want an approximation, of course, just like all the other problems, punch this into the calculator. Let's see, I'm going to do that now and give you an approximation. All right, so when you punch all this into the calculator, you get approximately equal to 8.4833, all right, which is an approximation. Awesome, guys. This is as challenging, I think, as it gets when you're solving an exponential equation where you have to take the log of both sides. I think this is how challenging it gets. Okay, the last two examples are applications. Let's look at those now. How long would it take? Stop right there. They're looking for what? What's the variable? What's the unknown? Time. That's what you're looking for. How long would it take? How long would it take to double an investment in an account earning 5% compounded daily? Now, compounded daily is a huge hint. Compounded daily means we're going to use this formula. Do you remember it? A is equal to P times 1 plus R over N. Do you remember this from the previous lesson? All to the power of N times T. This is the formula for the amount of interest is being accrued and how much is in an account, right? So here we have to identify some things, okay? Now, first of all, your rate is right here. This is your rate here. Let me see if I can. This is your rate, 5%, right? We're going to want to write that as a decimal. Now, compounded daily, this word daily here is your n value. How many days are in a year? 365, right? So n is equal to 365. Cool? Now, this next part is important. What do we plug in for A, and what do we plug in for P? Well, let me see if I can explain it this way. Whatever you plug in for P, the problem says, how long will it take for your investment? And P stands for your investment. P stands for your starting amount, if you will, like how much you are investing, right? So that's how much you're starting with. And at the end of the day, you want this to double. So whatever you plug in for P, the amount that you want to end up with is double that amount, right? So for example, if you let P be, I don't know, I'm just throwing out a number, $1,000 is your investment. You want it to double, which would be what? $2,000, right? A would be $2,000. If you let P be, I don't know, $5,000 for P, then A would be double that, which would be 10,000. Whatever you consider for P, A has to be double that amount. In other words, when you say double something, that means you're multiplying by 2. So what we can do is we can let A be double whatever P is. Yeah? All right. So they didn't actually give us a P amount, but what they did tell us is we want that P amount at the end of the day to be doubled. Yeah? Okay. So let's keep going. R is your rate, which is 0.05. Be careful there. N is 365 because it's daily. And then this is 365 times, now well, here we go, T. T is your variable. You're trying to figure out how long it's going to take for your money to double. All right, so I hope that setup there was clear. Okay, let's go ahead and solve for T. This is an exponential expression, or exponential equation, really, because your variable is up here. It's an exponent. So you and I are going to have to figure out a way to isolate T, to solve for T. One thing I suggest to do in the very beginning here is to go ahead and divide both sides by P. Divide both sides by P. If you divide both sides by P, notice that this P divides out with that P divides out by that P, right? And so all you're left with is 2 is equal to 1 plus 0.05 over 365, and all of this raised to the power of 365 times T. Okay, guys, all of this expression down here is being raised to this power with your variable. So I think at this time we're going to want to get this power right here to come down. How? By using the power rule for logarithms. If we take the log of both sides, then the power will come down. So let's take a common log of both sides. Or natural log, it's up to you, doesn't matter. So log of the left, log of the right-hand side. Okay, log of all of this. Okay. Because you've taken the log of both sides, we know the power rule for logarithms says that your exponent, which is 365t, can come down here. And then you have log of 1 plus 0.05 divided by 365. I'm trying to save my calculator for the very end. Now watch this, you guys. You're trying to solve for t, right? Your variable is right there. So why don't you divide both sides by 365 and also all of this to get rid of t? All of this at the end of the day is just a number. And of course, so is 365. So why don't you divide both sides by basically everything except for t? Like that. And the same thing on the right. Oh my gosh, can I fit it all? I'm not sure. Here, let me move this screen to my right a little bit, right? And make sure I can fit all of this in here. Okay, so then it's going to be 365 times log of, I have 1 plus 0.05. I'm trying to squeeze all of this in, okay, so bear with me. Divided by 365, right? There. Okay, I know it's a little squeezed in there, but so then all you're left with on the right hand side is t. So then we have t all by itself. T is equal to all of this, guys. All of this gives you your t value. So then t is equal to, let me write out this long denominator first, 365 times log of 1 plus 0.05 divided by 365. All that's the denominator, and up here is just log of 2. This is how many, what is it? Time we're looking for? Okay, so this is how many years it's taking for your investment to double when it's earning 5% compounded daily. All right, now you probably are expecting what's coming next. We should punch all of this, of course, into a calculator and see how many years this is, okay? So you're gonna have to be super, super, super careful here to get the right answer, all right? So you're definitely gonna have to use parentheses, okay? Parentheses. So you're gonna want to, in your calculator, punch in log of 2, and then click or punch in divided by, and then open parentheses, put 365 times log of, put all of this in, right, in your parentheses there. So let me start over. Log 2 divided by, open a set of parentheses, 365 times log of, a new set of parentheses. A lot of times your calculator will give you those parentheses anyway. Put all of this inside of those set of parentheses, close that out, close out the second set of parentheses, and press equal. All right? So let me see if I can write out what I just said in another color just to show you that I'm punching this into my calculator. So t is going to be, this is what I'm going to put in my calculator. Log of 2, and then I'm going to put divided by, and then I'm going to open parentheses, 365 times, and then I'm going to put log of parentheses, and then put all this 1 plus 0.05 divided by 365, close that parenthesis, close another set of parentheses there, and then press equals. Okay, guys, if you did all of that, you should get approximately equal to how many years? 13, I'm going to round, okay? About 13.86 years. Please put in years. That's your units, okay? About 13.86 years is how long it's taking your investment to double. That was a really cool example, a really cool application. Okay, you can imagine how many applications are out there for how many years will it take me to get this amount in my retirement, or how long will it take for my investment to triple, or whatever. A lot of applications in finance. So this is really, really cool. Let's look at one last one. Look at this last question. How long would it take for $500 to grow to $750 in an account earning 6% compounded continuously? Did you catch that last word, you guys? Compounded continuously? Because they're asking about compounded interest when compounded continuously, your formula, do you remember, is P times E to the power of RT. All because of that word continuously. Okay, let's plug in some values, okay? You want your account to grow to 750, so that's what goes in for A. Your starting amount is $500, right? That goes in for P. E is a number, a rational number. Your rate is 6%, which of course as a decimal is 0.06. And then T is unknown. You don't know how long it's going to take. That's what you and I are trying to solve. Cool. I hope you did well there. To get us started here, I suggest that we divide both sides by 500. Okay? Cool. This will definitely isolate our exponential expression on the right. So that's by itself over there. 750 divided by 500, I believe it's just 1.5. 1.5, okay? 1.5. Cool. Now you want your variable to come down, right? Just like we have been doing all along. Now the thing is, you need to take the log of both sides. But because your base is e already, do you know what kind of log we're going to take? The natural log of both sides. So let's take natural log of both sides. We did this earlier when we had base e. Natural log of the left, natural log of the right. Cool. And by the power rule for logarithms, this means that your power comes down like this. Okay? Now, we talked earlier in an earlier problem of this section that this here, the natural log of e, just means what do you raise e to in order to get e? To what exponent do you raise e to get e? Do you remember what we said earlier? 1, that's right. So the natural log of 1.5 is equal to 0.06 times t times 1. 1 is the exponent to which you would have to raise e to get e, all right? So we have the natural log of 1.5 is equal to 0.06 times t. You know what we need to do next, right? Just divide both sides by 0.06 to isolate t. So then our final answer can be rewritten or be written as t is equal to the natural log of 1.5 divided by 0.06. Cool. Let's punch that into a calculator and get an approximate number of years. All right, this is about 6.76 number of years. That's how long it's taking for $500 to grow to $750. That's really cool, you guys.